As I was running behind, I had a bit of an emergency and I wasn't able to make it back on time. So this is why I wasn't able to make the 9 a.m. tutorial. So, but since I recorded, I'm repeating the same tutorial now. So this is why I recorded. So those who couldn't attend, those who were at 9 a.m. tutorial who could not attend today, they don't miss the information, because obviously this is, I want to discuss some things that went a bit strange in the midterm, and then obviously how it's related to today's content. So yeah, I apologize for missing my 9 a.m. tutorial. I had a bit of an emergency, so I was not able to attend this week, but next week I'll be in person. So next week, every class is in person. But anyways, the midterm was posted recently, midterm results. And one thing that was kind of a source of confusion for students was actually 5C. And that question was asking the distinction between why the p-value was significant for the paired t-test, but it was not the independent t-test. And a lot of people thought a lot of students thought it was because Welch's t-test is assuming unequal variances, but the paired t-test is assuming pooled variance, and that wasn't quite it, because really the real difference is an independent versus dependent assumption, right? So when you assume two things are dependent, you're taking a difference of the two measurements, and then the actual variance is coming from the variance in the differences. So you're looking at it within difference variance instead of between difference variance between two different groups. Whenever you have a within difference variance, when you're looking at the variances between different buildings, so in the example it was different buildings, instead of looking at the variance between different groups of buildings, it makes the standard error smaller when you're looking at within differences, right? Like when you're looking at the variance, you're looking at the variance variability within the 8 different buildings. So looking at the variability, but when you assume that they're independent measurements, right? It turns out your standard error is actually smaller. And because the standard error is smaller, when you look at the denominator is actually smaller. So the t-test is actually being bigger, right? So when you have this thing that looks like this, t is equal to, your difference, right? This thing is actually smaller when you have a paired difference in relation to when you have an independent difference. And because of that, the t-test is actually made larger. The t is made larger when you have a paired test. And when it's larger, it results in a smaller p-value. Why? Because then it's further into tails, like maybe over here, which results in a smaller p-value. So that was the answer. And I don't think anyone got the answer. But the reason why I brought it up is because in this class here, the distinction between what we talked about earlier and now is that we're looking at 3 different groups instead of 2, but the same rules apply, right? So your test is significant if your t-test, or in this case, your f-test, is actually in the tails. So a small p-value must mean that the ratio is big because the numerator is big, right? So this is something to think about. If that question comes up again in some variation, it's because the numerator is bigger than the denominator. And that means the variability that's happening between the difference itself is bigger than the variance that happens from the noise space. So the within group variance is smaller than the between variance you see in the treatment effect, right? So the same thing would apply in the Anova test. So I want people to understand why that went wrong in the test. So yeah, so look at the solutions. Try to see where things went wrong. Another thing that was a bit strange is when people were answering questions about the left skew, a lot of people said that the lower values are low, and that does not characterize a left skew. So it's not that the lower values are low. It's not that the upper values are low. So a lot of people said the upper values are low and the lower values are low, but it's not that the upper values are low. The problem with a left skew is that really a problem is it's not centered, obviously. The thing with the left skew is that all the upper values are crunched up in the same area, right? So when you go left, a left skew thing means you have something that looks like this, right? So all your upper values are crunched up in a small window, where it's not, whether it doesn't really matter whether they're low or high, but they're all crunched up in a small area. And that's what makes it has a short upper tail, right? So it has a short upper tail because they're all crunched up in the same bin. It's not that it has low values, it's crunched up in the same area. So you have a short tail in the upper region, right? That's why it's less skewed. And that was really the answer we were looking for. It's not that it has lower upper values. So keep this in mind too. So those are two things that were a bit strange that I thought I'd point out. Okay. So back to today's lesson. So today we're talking about Anova and what makes Anova different from the t-test that you're looking at 3 different groups. So there's a test for this. The reason why we use Anova instead of looking at different pairwise tests is because if you keep doing different pairwise tests, you actually increase the odds of finding a significant result, even when it's not statistically significant, right? So if you have too many independent tests, you're more likely to find and fail to reject the null hypothesis. Sorry, if you have too many tests you're performing, you're increasing the odds of finding a reject the null hypothesis, even if it's not necessarily true, and that's the problem, right? So we have to adjust for the fact that you've done too many tasks. So the Anova allows us to make sense of potentially performing too many tasks, which essentially fishes for reject the null hypothesis that really isn't there in nature. Okay, so I'm going to use the empty cars example because I've been doing that a lot. You'll see that I'm going to use a cylinder. So cylinder class has 3 different levels. It has 4, 6, and 8. This refers to how many cylinders it has in a car. You can imagine that the more cylinders you have, the more your car is going to weigh, right? So you can imagine that the weight difference between, let's say, 4 cylinders and 8 cylinders will be quite a lot, right? I put as dot factor because you can see 4, 6, and 8 are numerical values. If I don't factor it, it will take an average when I want it to actually recognize the different levels. Like it's categorical, right? But I wanted to see it's categorical instead of taking averages because it's a quantitative variable, right? So this is why I do as dot factor. Anyways, if you plot this, so I'm going to make obviously a box plot because I want to see if the 2 things. I want to see if there's a significant difference in the distributions of the 3 different things. Like, is their variance quite extreme between them? And then the second thing I'm looking for, the obvious thing, is their mean difference is kind of significant, right? So significant mean difference would probably happen when you don't have overlap between the groups. You can see here that certainly the spread of, like, let's say 4 is bigger than the spread of 8. So that means that they probably don't have equal variance, and we have to be picky about this. This might mean that whatever test we do, we might need to account for the fact they don't have equal variances. But then more to the point, you can see that the means are not the same. There's no overlap in the distributions, right? So it's clearly true that, like, 4 has a lower weight than 6, which is a lower weight than 8, and the difference between 4 and 8 is quite extreme, right? So, and we can pictorially see that probably we're going to have a significant difference between 2 different groups, but it's not enough to just say pictorially we see that the means are different. We have to actually statistically show that it's true, right? So the one idea you might have is to use what you know. What we know is to perform independent t-tests, right? These are independent groups, right? Your instinct might be performing a Welch's t-test because you can see that the means are not, you can see that the variance is not the same across different distributions, and so you cannot assume equal variance. But the problem is that if you do a pair t-test too many times, you actually, so this is essentially because you have 3 different groups, you perform 3 factorial tests. The 3 factorial tests means you have 6 different tests you're performing, right? So you, for instance, the difference between, you have 3 different tests performing, right? So 3 factorial divided by 2. The reason why I divided by 2 is because you can imagine that some of the permutations are the same, right? So 1 and 3 is the same permutation as 3 and 1. Similarly, 2 and 3 is the same as 3 and 2. So to avoid having situations where I'm looking at the same pair twice, I have to divide it by 2. So you actually have 3 different tests performing. The problem is that so I'm going to load the page. You're going to see what I wrote a mathematical expression here that I want to show you guys. There's a fundamental problem with taking too many different t-tests, right? The problem is that each t-test is independent, right? So with 3 different t-tests, what we actually have is the following problem. You'll see that, sorry, it's not necessary. You can see that the probability of having at least one significant result, basically, right? Well, it's a complement of having no significant results. That's just something we know that's either A or not A. So have one significant result is equal to 1 minus the probability of having no significant results, right? But what is the probability of having no significant results, right? It is the complement of 1 minus 0.05. You might say, why is it the case? it's because you reject the null hypothesis when p is less than 0.05. So significant result. So no significant result is obviously the complement of 1 minus 0.05, right? So again, I mean, the reason why probably if no significant result is 1 minus 0.05 is because you reject the null hypothesis when p is less than 0.05, right? So what you have is 1 minus 0.05 to the power of n, because each test is actually independent, right? So what you actually have is 1 minus 0.05, the power of n tests you performed, basically, right? You can see that if you even have 3 different tests, your odds of rejecting the null hypothesis is actually 14%, which is too high, right? So that's actually and this is just when you have like 3 tests. If you increase your test to, let's say, infinity, because this is less than 1, because 1 minus 0.05 is less than 1, you can see this geometric series will converge basically, right? In the limit, right? Will converge in the limit because it's less than 1. This whole thing will, so the probability of having at least 1 significant result will eventually be 1, right? It will keep getting larger and larger until eventually goes to 1. So if you perform too many tasks with probability of 1, if you take n to infinity, you will find a significant result, even if it's not true, basically, right? This is why we cannot perform too many t-tests. You will find a result that's significant, even when it's truly not true in your data, right? So we have to have something else that allows us to control for this, control the scale for this, increasing odds of seeing a significant result just because you perform too many tests, basically. And you can imagine that if you have more than 3 groups, this really drives up the odds of seeing significant results. And in nature, you might have more than 3 levels in your variable, basically, right? So we can't do this. This is why we have the idea of Anova, right? Because it allows us to compare more than 2 groups without needing to perform too many different tests. But there's a caveat, obviously, because Anova only tells you if there is a significant result. It will not tell you where exactly the result is significant in, right? So it will not tell you exactly which group is significant. It will tell you that there is a significant group, but you have to do a bit more work yourself, right, to figure out where it is, basically, right? So how does this work? You have to have a null hypothesis, and it kind of works similar to the t-test. Well, obviously, if you want to find there is a significant difference in the groups, and we suspect that there is from our data, you can't assume what you want to show. So the research question tends to usually be the alternative, and the research question is that we don't think it means the same because we can see pictorially it's not, right? So we're going to assume a null hypothesis that they have the same group mean, but obviously we're suspecting that it's not true. The alternative, we want to find a p-value that's less than 0.05 so that we can reject the null hypothesis. Okay, so let's do an Anova. I set this up. So this is, you can see that I'm looking at the weight. I'm looking to see if the weight is different across the different cylinder classes, right? That's why you can see it says weight as a function of the cylinder class here, right? And I'm going to do a summary of the thing. So you can see here that the degrees of freedom is actually given to us as a function. So the degrees of freedom is what? Degrees of freedom between, which is the effect, is actually equal to k minus 1, where k is the number of groups, right? And then the degrees of freedom within is actually, and minus k minus 1. So if you look and see, you can see that there's 3 different groups. We have like 4, 6, and 8. So if you take the different, what you see here is that you have 3 minus 1. That's why it's 2 there. And then here, the sample size, I think, is 32. So we have 32 minus 3, which should be 30, minus 1. Sorry, it should be 29, right? So let's see what the difference is. Let me see what this is here. Let me see, 3 minus, oh, sorry. Let me just double check. What is sample size? Length of weight, let's see, 32. Okay, let me work backwards here for a second. The total degrees of freedom. So the total degrees of freedom, surely use my stylus pen here, but I don't have it on me. is equal to n minus 1. So that's actually 32 minus 1, which is 31, which makes this, I guess, 29. So the within is actually 29. So it's actually n minus k. There you go. There you go. Right, so it goes like this. So it's k minus 1 is the degrees of freedom for between the groups, and minus k is the degrees of freedom within the groups. So this is the variability you want this to remain low, right? You want this to remain low. The reason being is because f is actually equal to the ms between, I think they call it MSR divided by MSE, right? So you actually want this thing, you want the degrees, if you want the actual, you want the sum of squares to remain kind of low for this, because the ratio of these two things ends up being your F test, right? So you can see here that your F is actually equal to the following. So I'm just gonna keep this here. I'm gonna pull up another paint. F is actually equal to SS residual, so SS regression, I'm going to call it regression, which is the actual mean difference, divided by k minus 1, divided by SSE, divided by n minus k, right, which is actually equal to the MS regression divided by MSE. Right, so you can see that you actually want this ratio here in the denominator to remain small. You want this to be small, because your F distribution, which is actually kind of very right skewed, right, is actually going to be large when the denominator is small. So what it's saying is that if the treatment effect is significant, so the distribution looks like kind of right skewed like this, right? And it's saying, and it's kind of peaks somewhere around 1. It's saying if your mean difference is significant, then your numerator should be pretty high, because the numerator represents the variance you see between the groups, basically. Whereas the numerator, whereas the denominator itself represents the variance you see within each of the groups. And repeat again, the numerator, which is the variance you see between groups 4, 6, and 8, you want to be big because it would show you have a significant difference. The denominator is the actual variance you see within the variance you see in cars within each of the same group. So if you have a high variability between, let's say, the cars in group 4, a high variability within the cars in, let's say, group 6, and a high variability within the cars within group 8, if the variance is too big within each of the groups, it will obscure the difference between the different groups, right? So that means that if you look at the box plot, and you can see that the variance within each of these groups is too wide, so that it obscures the between group differences. You will have a very small F test, right? So a small F statistic happens when this variance you see within each of the different groups is so if it's very spread, like maybe it's very spread in the distributions, is bigger than the actual variability you see between groups 4, 6, and 8, right? So you would probably have a large F test here, because you can see there's no overlap in the distributions, but if the spread was so wide that there is overlap in the distributions, it would obscure the actual group differences, which would make the F test smaller, right? So you want the variability you see within each of the different groups to remain small. So between the group differences is magnified, basically, right? So if you look at this ratio here, which is the MSE, right? So this thing here is this ratio here. You will actually see that this 9.088 divided by 0.397 is 22.1. So if I just show you guys in R, you see that that's what they're doing here. It's 20, they're rounding, obviously, it's rounding up, basically, right? So this is what you see here. What's the problem here? Does anyone know what the issue is with this Anova test? What did I actually show? Anyone have any idea? So what did I actually show here? So obviously, because P is really small with this F test, probably our actual F statistic is somewhere in the tails over here, which means we're going to reject the null hypothesis. Yay. What does that mean, guys, to reject the null hypothesis? Does anyone know what the problem is with this conclusion here? Where is the difference? Like we reject the null hypothesis, which states that we have a mean difference somewhere. What does that mean, though? What's the conclusion we can make here? Anyone know? Anyone have any ideas? No? No ideas? That's okay, Eddie. That's totally fine. Yeah, it just means means are different. We don't know where the difference happens to sit. And the problem is that while we know the means are different because the p-value says that it's less than 0.05, we don't know where the mean differences exist. It doesn't tell you if 4 is different from 6, or if 6 is different from 8, or 4 is different from 8. It doesn't tell you where the mean difference happens to be that's significant. Just because you have a p-value that's less than 0.05, guys, does not mean that every mean difference is significant. Some may not be, right? Yeah, the null hypothesis is that all means the same. If you reject them, because this is a distribution, Eddie, along the null hypothesis. This is a distribution on the null, basically, right? So if the null is true, your actual F statistic should be closer to where the mode happens to be. The mode for the null is somewhere over here, and if your F statistic you get is close to the mode, it means that you don't have evidence to reject the null hypothesis. That is why the p-value is very high for a insignificant result. When you have an insignificant result, because your F or your T, whatever your t-test happens to be, is close to the actual mode, it has a high p-value, which means that you don't have evidence to reject the null hypothesis. Do you know what I mean? So when it's suggested that you're too close to the null, wherever it happens to be over here, and the chance that the null is true is still too high. So you will not reject the null hypothesis if the evidence is over here, suggesting that your p-value is your odds of making a mistake is still pretty high. You will only reject the null hypothesis when the p-value is small. Well, the problem here is that you don't know where the mean difference happens to be. It just tells you that some mean difference is significant. It may not be the case. It's possible they're not all. It's possible that not all of them are significant. Maybe you only have one significant mean difference and the other ones are insignificant. So you don't have the insight into which ones are significant. You have to do more work there. That's why we have the notion of a Tukey's HSD. Tukey's HSD tells us where the group mean difference happens to be. We can't assume they're all significant just because the p-value is less than 0.05, right? So that would be very incorrect. We have to do more exploration to determine where the difference happens to be. Now, if you have 10, if you do an F test and you're looking at 10 different groups differences, it just means that in the F ratio, in the F statistic you can construct over here, you would have degrees of freedom of 9 instead of 2 because it's k-1, and your F test would just reflect the fact that you have 10 different groups. You could have as many groups as you're comparing as you want to. You would just adjust your degrees of freedom, the number of groups you have, basically. The only situation where you would know where the group difference happens to be is if you're doing a group comparison of just 2 groups, right? If you're doing a group comparison of only 2 groups, of course you know where the difference happens to be because you're only looking at difference of 2 different groups. But the minute you introduce a 3rd or 4th or 5th group, you don't know where it happens to be. You have to do more work to figure that out, basically. No. You have to do a Tukey's HSD to figure out where it is. All right, so the Anova test doesn't tell you where the significance happens to be. It just tells you there happens to be one. You have to do some more exploration, basically. All right, so we don't know where it happens to be. So this is why we need Tukey's HSD. We'll put in our Anova into Tukey's HSD to figure out where the difference happens to be. If I run this, you get this kind of convoluted function here. But it does actually give you a lot, because not only does it tell you the difference, so you can see that we're looking at 6 and 4 here. The difference is 0.314156. You might wonder where that comes from, but you can actually check and see yourself that it's true, right? So if I take the mean, for example, of let's say the mean of so let's say I want to look. Let's say I want to look at the mean of just say. I should probably. I'll do a quick demo here to show you guys what I mean. Oops. Where was I? Yeah. So if I want to find, for instance, let's say, so weight mean, empty cars. group by, so let's say it's DYL. Oh, yeah, it's DYL. And then summarize. Oh, I spelled that totally wrong. Let me just check something. I want to see something. Where is it? Let me just use it. I totally haven't used the summarize function in a while. I want to show you guys something. It's on in here? No, I don't want to use base R. No, it's got to be summarize. Maybe it's help summarize. I totally forgot I'm determined to figure it out. I just want to show you guys that. Let me see. Summarize function in tidyverse. This is real time and real-time me troubleshooting, basically. Okay. Let me see. Because for some reason my thing is not. Oh, there you go. So let's steal this. Yoink. You can steal this here. There you go. So I was looking for the summarize function. There you go. Oh, look at that. It's working on the exact same thing as I am. Yeah, so you see I put Z instead of S. That's why I couldn't figure out what the heck was going on with my thing. Okay, so I want to find the mean of WT, right? So I want to find the mean of weight. Right? So let's run this. Oh. Oops. The other thing is I forgot to download tidyverse. Okay. There you go. Okay. Cool. So if I look at weight mean, you will see that you get the means of each of the different groups and their sample sizes. So there are like 11 in group 1, 7 in group 2, 14 in group 3. But anyways, you can see the mean of 4 is 2.29 and the mean of 6 is 2.12. So look at the mean differences you see over here. Where is it? You will see that wherever it happens to be, you will see that it's actually the difference of what you saw here, right? So if you just take a difference, for instance, of 6 and 4, you will see that it's 0.321. If it's a difference of like 8 and 4, you will see that it's 1.17. You can even see it, right? So this difference between 4 and 2 is almost 2, it's 1.71. So you can see that it gives you all the differences. And it gives you a lot lower and upper bound for the confidence interval, because you can see that in all these intervals, 0 is not in there. That is significant, right? So not only is the confidence interval telling you that the hypothesis is significant, that the alternative is probably something you want to conclude, because 0 is not in there. So the confidence interval tells you what the plausible values happens to be for the mean difference. And you can see that among all of these things, 0 is not a plausible value. Right, so if 0 is not a plausible value, that would suggest that you have a pretty significant result, because 0 a mean difference of 0 is not something you necessarily see. Right, so the p-value is significant for all of them, but is in fact especially significant over here. Right, it's especially significant in between 8 and 4, where you have a very big difference, but it's significant in all of them. So where is significance? It's significant in all of the actual group differences, in fact, but it's the most significant between 8 and 4, which you kind of expected, because if you look at the actual plot here, you can see that it's quite far between 4 and 8, right? Okay, now let's go a little bit further, because one thing I do want to point out is that all of the p-values you can see here in the pairwise t-tests is actually bigger than your grand p-value. So the p-value you got for this is a lot smaller than you got here. This is because this is adjusting for the fact that this is like doing a Bonferroni thing. Tukey's HS does a Bonferroni adjustment to adjust for the fact that you did too many tests, basically, right? So you can see that it will adjust by the power of how many different tests performed. And that's why your p-values are actually bigger here than it is in the overall grand ANOVA. But we can ask ourselves if this is actually appropriate, right? We could ask ourselves, logically speaking, if the test was valid. And by my asking, is the test valid? I mean that, like, is it true that we actually have equal variance, right? So this is something that was something we asked in question 5D. They said that one thing you might want to check about the ability of your test for the pairwise t-test, whether or not your distribution was normal. But something else you could have checked as well was if you had a Welch's test, at least, is if equal variance assumption was appropriate. Some people said that some people said for the midterm test, check to see if you have equal variance for question D and in part 5, which was not appropriate because the test we're using for the different buildings was not actually a Welch's t-test. It was actually a pair t-test. So the thing we cared about was normality. But here we want to look for two things. So because we're looking at differences in independent groups, we're interested in whether or not the mean differences are actually normal. And then also we're interested in whether or not we have like variance being equal, because that's an assumption that ANOVA actually assumes you have equal variances, right? So, and if you don't, you have to adjust for this in your task, right? So I'm gonna do a QQ plot, and I'm gonna put a facet wrap. So facet wrap is a new feature you guys are seeing here, but facet wrap allows you to compare. So if I just do this, right, it will just give me the overall. It'll just give me the overall. Oops. It'll give me the QQ plot for weight, but it won't actually factor according to the different classes, right? So you see, we'll just do this, which is not what I want. I want it to look at it according to different classes to see what I get, right? So when I put a facet wrap, it will factor according to different groups. You can see that for group 4, it's okay. Even for group 6, maybe it's okay as well, right? There's a point off the line here, but it's not so gregarious, so we would necessarily think about it too much. But the problem is kind of here. There are a lot of outliers in group 8, which might make us raise our eyebrows a bit as whether or not we should actually really use the equal variance assumption. If we, right, and really, I guess if we should use a normality assumption. If your distribution is not actually normal here, one thing we have to do is probably use we should probably use the median, right, to assess the differences instead of using the mean. So this is why I'm going to bring up moods test. I don't think you actually had moods median test in your exam, because maybe it was too early to think about that kind of stuff, but you probably will have it for the final exam. But you see that if your QQ plot reveals that you don't have something that looks normal, you probably shouldn't use, right? You probably would be suspicious over here, example, especially, right? You can see there's a lot of outliers in group 8, so we might want to think about some. So there's two things to do. Let's suppose we performed a Welch's task because we knew that the variance is not the same. We could see if that alleviates the problem, but really I suspect we probably have to perform a moods test because obviously we don't have a normal distribution. So you can see that the Welch's t-test only really works if what you see is the distribution for all these things are turning the line, but the standard deviation perhaps is not consistent across the different groups, right? So, but you can see that with group 8, there's a bit of a problem. But anyways, let's pretend that Welch's test is okay. There's a library you should install. It's called PMCMR plus. This is so I'm going to do a one-way. So I'm doing a one-way test here. I'm looking at mean differences, right? So you can see that first it does the test. Right, and then I think afterwards it does it. So let me just do this. You can see here that this is the analysis, not assuming equal variances. You see how the denominator degrees of freedom is a bit different from what it was before, right? So now it's like 18.974. It's a convoluted formula. The p-value is really significant still, but not to the same extent as before. It's actually slightly less significant, but it's still very significant, right? Saying that there is a difference somewhere, but like before, you don't know where it happens to be. But the difference is we don't use the Tukey's HSD because that's assuming equal variances. You have to use the Howell's test instead, because you cannot assume, you cannot use Tukey's HSD, which is assuming equal variances. You have to use Games Howell test instead, right? But you can see that. Oops. Why not? So weird. There you go. Okay. Sorry, guys. It's gonna run the whole thing over again. Yeah. There you go. You can see that. So here, oh, sorry. Here it does the so this is the games HAL t-test or the games HAL test. It's actually showing this 2x2 table. There you can see that obviously the reason why this is a dash here is because you cannot compare 6 to itself. It doesn't make sense, but you compare 4 to 6. You can compare 4 and 8 and then 6 and 8. This is again why you have it. 6 is the reference group, I think. This is why you see that there's a dash here. They chose 6 as the reference group. Doesn't really matter, it's arbitrary. You could have chosen 8 or 4. Anyways, you can see that 6 and 4 is still significant because it's less than 0.05. 4 and 8 is the most significant, obviously, because obviously you can see that it's the -6. This is also significant between 8 and 6, right? But the difference between 4 and 6 and 8 and 6 is certainly less significant than 4 and 8, which we expected, because if you look at the box plot, you can see that 4 and 8 is probably quite wide, right, in terms of the difference between each other. But you can see that all these p-values especially are a lot bigger, right, than the previous ones, I believe. Let me just double check. Here they are. So 4 and 6. Yeah, you can see that they're almost twice bigger, right? So that's because the standard error is actually bigger under the unequal variance assumption, so it will pull the t-test down. But logically, that makes sense, right? Because in the denominator, if your standard error is bigger, which it will do when you have unequal variance assumption, it will pull the t statistic down, right? Because you can see that t is a ratio of the difference divided by standard error, right? So that's why you can see the p-values are actually smaller when you have equal variance assumption. That's actually why. Yeah, that was why for question C, you actually saw that the p-value was not significant when you use Welch t-test, because when you assume unequal variances in independent groups, it will make the standard error a lot bigger than it would be for a paired t-test. So it resulted in 2 different conclusions. Okay, but we copied this back from the actual GG plot here that's inappropriate of a test to use, because Anova is really assuming normality assumption. And even Anova, where you have unequal variances, still assumes normality. But the problem is that from our QQ plot, we can see that it's probably suspicious, especially here, even a little bit here. It's whether or not our assumptions are actually right necessarily valid. So we should probably try to use Moods test. So what the Moods test does is it compares it looks to see for all the groups you have, be it 4, 6, and 8, which of them have medians that are bigger than the grand median, right? So 4 is different from 8 if the proportion of times 8 is bigger than the grand median is significantly bigger than the number of times 4 is bigger than the grand median, and same with 6 and 4 and 6 and 8, right? So if 6 is bigger than the grand median more times than 4 is, and it's significant, you would see a p-value is small. And similarly, if 8 is bigger than the grand median more times than 6 is, you would see a p-value is significant. So that's why we look to see what the grand median happens to be first, because we're going to evaluate true and false statements to assess the proportion of times, right, you have certain groups are bigger than the median. So I took I called M the median. So you can see that I'm summarizing the median. Then I pulled the median to a value called M. So you can see that when I just type in M, it will tell me 3.325. That pull just puts it to a letter, right? It pulls the actual median and stores it in a letter. Okay, now let's create a table with our data. So this is saying, put it within your empty cars, look at a table that tells you the number of times your cylinder class is bigger than the median for weight, right? So how many times your weight bigger than the median for each of the cylinder classes. If I run this, you'll see that It's false for 4 because it's never bigger than, it's false 11 times, it is 11 times, and true 0 times, because for 4, it's always consistently smaller than the median, right? And you can see that 4 is so low that, of course, the median of 4 is lower than the median of all of them. And so you can see that for 6, about half the time it's not actually bigger. Half the time it kind of is, right? Because 4 and 3 are kind of close. And then for the last one, most of the time it's actually bigger than the median. One time it's not, basically. So the question is, are these differences in proportion significant, right? We can check and see. So we're going to assume the reference group is 4. That's why you can see correct. When it says chi-square test, correct equals false, it's saying that the default is that obviously false, right? And we'll check to see if the number of times the other groups are, says true is pretty significant or something. So let's see what happens if we look at in terms of the medians test, is actually within Ken's function SMMR is doing the same thing as the chi-square test, right? So he built the function that's doing the chi-square test. You can see that. Does anyone know why it says chi-squared approximation may be incorrect? There's a reason for this. Does anyone know what the problem is with this? There's a reason why it's saying this. Does anyone know why it says this? There's an assumption about the chi-square test. It's not actually being held in this table. Right, so the chi-square test says that you should have at least 5 cells. You should have at least a cell count of 5 in your expected counts. So you should have a cell count of 5 in your expected counts for all of the different cells, right? But you can see here that if there's an observed count of 0, an observed count of 1, an observed count of 4 and 3, the expected counts will themselves be less than 5. That's why I was telling you that your approximation may be incorrect. It's saying you don't have a large enough sample size necessarily, maybe, to get a good approximation of this test. Take your p-value as is. Take your p-value with a grain of salt is what it's saying. You may not necessarily have a big enough sample size to make sense of your data. Is what it's kind of telling you. For your information, if you guys are curious to why you get this sometimes, if Ken gives you small data sets to work with, it could be why that's happening, because he's not going to give you on a test, right? A data set that has like 1,000 points, so you may inevitably end up seeing that. It's not like your function didn't work, it's just your data is kind of small. So here's a chi-square test. The degrees of freedom is 2. Your p-value for the chi-square test, and by the way, the chi-squared is actually also a right skew thing, because the chi-squared is actually a square of a normal, which means that it is also kind of right skewed, or something like this. Oh, sorry. But the degrees of freedom will actually, I really should get my stylus. The degrees of freedom will actually change. It'll something like, sort of like this, I guess. But you can see that the degrees of freedom will actually change when your sample size is, when you have a lot of independent, when your sample size is large, your degrees of freedom will change. So if you drive up n, it may look something like this, maybe. Sort of still right skewed, but to a lesser extent. You see that it'll keep getting a little bit less skewed with increasing sample size. And maybe it looks like this for larger n, basically. So still right skewed, but not to the extent that this is. All right. Anyways, the median test actually gives you the same information. So look at what you see here. Then look at the p-value here. You can see that it's the same. And also the statistic is the same too. It's like 2.149. It's just rounded up here. It's the same test because the medians test is doing a chi-square test for categorical data. I mean, sorry, for categorical groups, because your variable cylinder is categorical. It's dichotomizing your actual your variable into different groups, and it's assessing the differences of the median across those groups. Right, so you can see that it's telling you have a significant difference in the medians, but you can actually see that again. You can see that pictorially. this is the actual plot of the medians because the medians sit in this black line here. And you can see pictorially that the medians are kind of different. Yeah, the medians test doing a chi-square test. You can see that, you can actually see that it's doing a chi-square test where it's on this table here. It's doing a chi-square test on the categorical, because the reason, once it actually converts this into, what do you call it? Into a categorical table where you're either above or below and you're in different groups. This is now a dichotomous thing, right? So you can see that above and below, you either are above and below, yes or no, and you have 3 different groups. These are both now discrete categorical variables, right? So you can use a chi-square test for testing the independence on categorical things. So once you dichotomize your variable, so you're looking at whether or not you're above or below the median, yes or no, the variables change from a continuous numerical thing to a yes or no. You're either above or you're below, and then you're grouping. So you can see this is very discrete in both of the variables. So then you can use a chi-square test. This is what the median test is doing. It's doing a chi-square test, which is on those 2 categorical variables to test if there is significant association between being above and below and your group. So it's trying to see, is there an association between being above or below the median and the class you are in, like the group. So those are the 2 variables, either you're above or below the median and you're grouping, and it wants to see if there's an association between those 2 things. So it's doing a chi-square test for categorical variables. That's why the actual test statistics looks the same. If you look at the chi-square test here, you'll see that it's doing the same thing as it's doing over here, right? So they're doing the same thing. But the issue is that, again, like before, it doesn't tell us where the difference happens to be. So we need to do it more based. So even the median test has a bit of work to do, where you have to do a pairwise median test. Now, unfortunately, when you do a pairwise median test, you are actually doing 3 different tests across the different groups. Like I said before, in going back to this thing here, this does increase the chance of finding a significant result. The way we adjust for this is actually you can see the Bonferroni here. So that you can see the p-value here that's adjusted is actually 3 times the number of the original p-value. The Bonferroni will actually multiply by the number of tests you performed. Right, so if you actually take these p-values and you multiply it by 3, you get these ones over here. So it's saying, okay, we recognize that we did too many tests. Let's adjust for this by multiplying by the number of tests we did. This will raise our p-values. And if our p-values are still significant after raising the p-values, and we really have a significant mean difference. If it's not, then it might indicate that we fish for a significant result that's not there, right? So the p-value is still significant even when you raise the values. So there probably is a significant result, and we saw it in the actual plots. Right? I did record this because the 9 a.m. class did not get to watch this. So I'm gonna post this as well on my GitHub. So if you want to watch this again and you want to play with the code, you are more than welcome to do that, because I will have this up maybe in an hour or 2, and you can tell everyone who's not in 9 a.m. class, I profoundly apologize. I had a family emergency and I could not attend this morning, but I did record and put a lot of thought into my layout so that way that they can follow the lectures, because I know it sucks not to be able to ask questions in live time, and I apologize. So I will post all these things. Everyone, and have a great day, guys.